So indeed, you're going to hear about Dash. I hope most of you have not heard this before. Some of you I'm sure have, but there are some new things here. So let me, before starting, thank Sebastian Gomez, who I think I saw here somewhere. There he is. And Ed Loss, who's, I don't know if he's here today, but Bob Simcoe, I should have put his name on here as well, who is the designer of the scanner and the plate cleaning machine. There's Bob over there. And many others. So this has been a project that's taken a lot of people and a long time. Jessica was involved in the early days, still is, lots of people. So what I'm going to show you today are early results and then current results that we're now getting. So let's begin here. And now I don't. Sorry, this thing was working. Amazing. Okay, there we go. Nope. All right, no clicker. That's not good. This is weird. Huh. All right, well, I'll just do it the manual way. At least the pointer works. Yes, pointer works. Okay, so on we go. There we go. All right. So here's what we're going to do. I'm going to tell you about how Dash works and some early science that many of you will have heard a bit about, but I'll remind you. And then get to the, and I'll spend a bit. I think the abstract I wrote up said I would say something about the flood recovery. I decided there wasn't room to do that. I'll make a comment when we go along because, well, let me make it right now because there's too many other things to talk about. If you now, walking through the corridor, the glass part of the walkway from building C to D, and you look out at all this amazing construction going on out here, the hole in the ground, you can see the pipe that broke. I verified this with a workman this morning. I thought, am I looking at the pipe? And yes, you are. It's a big 8-inch pipe and right out, close to building C, and you can see the break in the pipe, which, as luck would have it or not have it, was facing the building, so 60 pounds of pressure. This fire hydrant just was blasting through all the earth and flooded us out. But it's all being fixed, and as you'll see, we have recovered from the flood. We're back scanning. There's some dates that I'll show you later, but in short, we hope to finish this whole thing in about 2 years, 2.5 years, probably more realistically. So I'm going to tell you about a survey that we've been one of the prime motivations for Dash, looking for black hole low mass X-ray binaries by their historic optical outbursts. Dash is an optical time domain survey. And then I will also show you some results towards the end on a couple of AGN, 3C273, OJ287. I didn't include what I mentioned in the abstract, possible binary periods, and a couple of other AGN. Again, I think there isn't time to do it justice, so that you can save that for another time. Okay, so just to remind you, black holes, of course, are by definition almost highly variable objects. The first one was discovered. Harvey was very much involved with this, SIGX-1, by the variability of a state transition, which we knew nothing about back in the early 70s, which revealed SIGX-1 by a radio source appearing. Now we know a lot more about that correlation. But apart from SIGX-1 and one other high-mass X-ray binary with a black hole that I'm not going to talk about, and a new one that Sebastian and I are working on that we'll talk about some other time, we think we have another high-mass system. Apart from those, all the stellar mass black holes, just to remind you, are in LMXBs, low-mass X-ray binary systems. And they're all transients. A couple of them, without going through the detailed list, are transients that have been stuck on. GRS 1915 is the prime example. It was never known before 1992. It appeared, a very abrupt outburst, and has been on ever since, and a few others. GX339 is basically a persistent source, although it undergoes transitions. But the other 18 to 20 dynamically confirmed systems, and another 40 at least now, very likely systems, are all transient systems. And just to remind you, the same physics may or may not be involved, these transient outbursts, with what we see in AGN, which are on for relatively short lifetimes. They're not on persistently. So the whole time domain characteristics of both stellar mass and supermassive black holes is a key part of the way we understand these systems. And now, once again, this bloody thing is not clicking, so this is really getting irritating. Okay, so this, as I just said, there are 18 dynamically confirmed systems, another 40, 42, total of about 60. And this should surprise you if you haven't thought about this before, that there are this many black hole systems with still only roughly 150 neutron star systems. This is a problem that's bothered me for a number of years, and I'm sure others in the group here as well, because right away that tells you something interesting is going on. The black hole production from initial mass function arguments, and I'm going to get to those in a bit here, would lead you to think that there should be many more neutron star systems. But within a factor of 2, roughly, maybe a factor of 3, they're comparable numbers. And what's also been a real challenge to understand is how you make the LMXBs generally, but particularly the black holes, because as we get a significant sample, and there are, as I keep saying, 18 of them that we know are black holes and another 40 that very likely are, they're all very similar. They've all got low mass, typically K-dwarf companions, which are 0.5, 0.6 solar mass stars. Some of them may have, some actually do have slightly more massive companions. I'll show you a cartoon of one in just a second here that's roughly 1.2 solar masses. But how do you pair these very low mass stars with 5 to 10, or in the case of GRS 1915, maybe 12 to 14 solar mass black holes? We're going to come back to that in just a second. And so these are I'm just reminding probably many of you, most of you, of the challenges that these systems present, but also the fact that they're all transients tells us that we have a very incomplete understanding of the population, because most of the time they're in quiescence and we don't see them. Prior to what we're doing with NASH, 3 of this population have been detected historically. But beyond that, this whole population, we don't know what their recurrence times are and what the total populations are. So just to remind you what these things might look like if we were up close, here's GRO 1655, discovered with GRO, hence in the source name in 1994, in an outburst, and not known beforehand. So just to finish the introduction here, the way that the community has generally considered the origin of these systems, the low mass X-ray binaries now, we're not talking about the high mass system, they have a much more easy to understand origin, is that they emerged from primordial binaries, pre-existing binaries, which, and this is the hard part of this whole story, were originally a low mass twiddle 1 solar mass star with a twiddle 15 to 20 to perhaps 25 solar mass massive O star, which became either the neutron star or a black hole. And the miracle that I'm being a little bit poking fun at this, but not that one should, because it's still considered by, I think, most people in the game to be what's fundamentally going on. But the challenge is that you have to keep this very low mass system, which is now going to in-spiral through the very large envelope of the supergiant, and expel the envelope. This is common envelope evolution, but you've got to expel a considerable amount of mass with the binding energy that mass represents from this relatively low mass companion without merging in the core. That's the challenge. And unfortunately, it's never been done theoretically, which might surprise many of you. It surprised me when I really understood this a bit some time ago. It's a very difficult dynamical simulation to follow all the way through. So it's not surprising it's not been done. So it hasn't been demonstrated, although many, many papers have been written. So common envelope evolution was invoked for these systems because it almost certainly is what's going on with cataclysmic variables, CVs, but then it's a much easier job. We're only trying to expel a half a solar mass. We leave behind a 0.6 solar mass white dwarf or whatever, or depending on the mass of the progenitor, of course. So the energetics are much easier. And so because of this, there have been recently, and going back even much earlier than these references I've just put here, other models proposed for how you make these things. I've been thinking about and working on a bit another version of something that was presented by Haggai Peretz a couple of years ago, a year ago, and a student that are dynamical formation models. But this is an interesting one, but I think there's an even better way of doing this by doing exchange collisions of a single black hole with pre-existing K-dwarf field binaries. But that's work in progress. So finally, just to finish here, this whole common envelope evolution, if it is involved with making these, despite the difficulties I mentioned, it should be even more difficult for black hole systems than neutron star systems, because you're expelling more mass from the envelope. They're more massive progenitors. So these are all the challenges that there is, it's unbelievable. There's something that keeps popping up on the screen here, which interferes with. Okay, so this was one of the motivations for DASH then, to be using this enormous plate collection here that we've got here to digitize this collection to, among many other possible projects, and there's no end of things that one could do with this data, to look for historic outbursts from what we have recognized in X-rays as black hole LMXPs. The same could be done for the neutron star systems. It's a more difficult thing to do for them because their outbursts are typically not as large in amplitude, and the quiescent magnitudes for either the neutron star or black hole systems are very faint. So with the limited sensitivity, and I'm not taking the time to show you what the range of sensitivities are, but you'll see that in a few of the slides coming up, it would be more difficult to see neutron star outbursts. But the neutron stars, as we're going to see in just a few minutes here, are undergoing outbursts at a much, much higher rate than the black hole systems. So it's the rarity of the black hole outbursts, the very short on times, if you like, duty cycles, that have motivated this project. So the plates are full sky, and we've got this enormous collection, so what can we do with it? And, okay. I'm going to skip through the history here because most of you have seen this. So that was an early picture of right outside here. And very quickly, just to remind you, the plates were taken with a whole series of telescopes. It may surprise most of us that there were actually some 80 different plate series involved, but roughly 10 are the principal plate series, with fields of view per plate of roughly 4 degrees to 30 degrees. So with the 30-degree plates, you're repeatedly covering the whole sky with this very large number of plates in these so-called patrol plate series. All begun by Pickering, Edward Pickering, the HCO director from 1878 to 1921, so 45 years or whatever. And he did this because even then, in the 1880s, the origin of variability in variable stars, which were known, was completely unknown, except for Newtonian physics and eclipsing binaries, which were certainly understood. So it was that motivated this whole thing of doing repeated exposures over and over and over on the full sky. And wonderful that he did this. And these are these historic pictures that I think we've all seen many times, so I won't spend time on them, but it was a great body of work that produced this enormous amount of plates. And what is wrong with this thing? Sorry. Okay, I was just going to show you here what the plates look like, and of course all you have to do is go across the hall to get this view. But let me show you a plate that we have recently identified, which is what I'm showing you here, which is a plate from the so-called B series. This was done with an 8-inch Clark telescope in Peru, the B series plates. And this particular plate is actually very historic, so we're not scanning this one. Scanning the plates means that we clean off all the markings. The markings would raise havoc, as you could imagine, just staring at this plate, with trying to digitize these 100,000 images of stars, which of course you can't see from back here, but this plate probably easily has 100,000 stars on it. And all those markings just completely mess it up. So we've, in the very beginning, set up a program that would save the historically most significant ones, and this one surely qualifies. Sorry?
What are the markings?
The markings are they're marking stars that, in this case, Henrietta Leavitt was working on. This is the Small Magellanic Cloud, and this plate is actually her markings of identifying Cepheid variables that she made her wonderful period luminosity relation discovery. So this is typically what the plates look like, although this is more heavily marked up than most of them. But what they're doing in this little region here, there must be a Cepheid here that she's working on, and all these surrounding marks that are pointing to other stars are the secondary standards. So the stellar magnitudes were inferred by measuring image diameters and interpolating on a sequence that was carefully established and measured, but fundamentally, since it was only photographic photometry possible, obviously in the 1880s or even up till 1980, CCDs hadn't come in. So, but it was image diameter measurements that identified or allowed one to convert to stellar magnitudes. So that's what you're seeing here, a heavily marked up plate. And once again, sorry about this, there is a very irritating Xfinity ad that keeps popping up on the screen and blocking everything. Yeah, that would be a good idea. Well, let me not take the time to do it right now. Let's just keep going. Okay, so too much history here. All of the visual observing, of course, was wonderful. This collection's been used for 100 years and more, but why digitize it now? Well, these are all the obvious reasons. I won't take the time to go through them in detail, but the key thing to know, if you're interested in all this, is that this project became possible about 10 years ago because we had full sky photometric catalogs, actually longer ago than that with the Hubble Guide Star catalog, but thank heavens for the AAVSO down the street who carried out and are now about to release their DR10 for the APAS survey, a CCD full sky survey that does very accurate photometry. That means on every one of these plates with 100,000 stars, you've got 100,000 calibration points, okay? Or if you have 30,000 stars, or more typically 20,000. So you could calibrate the data, self-calibrate all over the plate, and do it in a spatially resolved way. And of course, the data quantity from a project like this is large. A petabyte is what we're going to wind up with. There's a third of a petabyte now on spinning disk that has been digitized with roughly a third of the collection done. And until 10 years ago or so, that was too much to think about, but now it's becoming increasingly natural to think about. And of course, the whole era of time domain surveys coming up with LSST make the project very relevant for complementing these things, large amplitude variables that are discovered, that have been discovered with PTF or the Zwicky transient factory now at Caltech, or will be discovered with LSST, are all interesting to look at with this database. So there are many reasons. And these are the key things that, of course, this long time scale buys you. You can look for what I was talking about a minute ago, these things that have very long recurrence times, they become observable. You can look for very extreme amplitude flares from whether they be stellar mass black holes or AGN, and any other kind of rare events. So just to name a few. So let's keep going here. And finally, this is a diagram that we put together a few years ago to sort of illustrate how DASH winds up overlapping with the modern surveys, and in particular LSST, coming up in a usual representation here of, in this case, recurrence time scale versus absolute magnitude. So there's considerable overlap. The difference, of course, so you can look at all these categories of objects, but what you clearly have for the plate data is much more limited sensitivity. So you're limited to much brighter objects. The range of typical B magnitudes that we reduce all the data in Johnson B system are typically complete to about 14th magnitude and extending down to 18th magnitude on the faintest end, but with decreasing numbers of plates. So, and once again, this is really getting, I should have turned off the internet. That's exactly what's bothering this thing. Okay, I'm not going to go through the scanner operation because there's too much else to talk about, but this is the original scanner. It's now been replaced with one that looks essentially identical but is improved and is slightly faster. But this is a remarkable machine that Bob Simcoe, sitting right over here, had the foresight to know existed, at least in principle, in industry, namely a very precision XY scanner. God, sorry about this. A very precision XY table that could move, in this case, a fixture that Bob designed, this whole top end here, roughly 40 pounds of aluminum, to 100 nanometer precision, so 1/10 of a micron. And that was required because what we're digitizing, the plates, two plates, one after the other in a continuous scan motion across both of them, which I'm not going to walk you through. We're digitizing into 11 micron pixels, and if you want to register the full photographic plate in registered pixels from one corner to the diagonally opposite corner, you better be at micron or better accuracy. And that's what this system does very, very nicely with a fixed CCD, very fast readout here, 4K by 4K system, to digitize a given plate in 60 different exposures, which are then tiled together to make one mosaic image from which the pipeline, which I'll show you very quickly here, operates on and is beginning with S-extractor, which is the primary engine of the whole system, to do object detection, and then a WCS solution on that fully detected plate image, beginning with Jessica's tools and carrying on with higher order fitting using SCAMP, which was worked on here some years ago. All sorts of complications for various things that were being done at the time with something called the Pickering wedge to do multiple images of stars on some plates to get an internal calibration system. All of that has to be accounted for. It's actually quite easy to do. And finally, photometry against originally the Hubble Guide Star catalog, now, as I've already said, the APAS catalog. And for the Kepler field, the Kepler catalog. But this is really the best one right here. And you need the metadata from all of these plates to be able to make sense of it. That's the only place the exposure dates and times are recorded. So all of that has to be factored in and is, and where we now stand is scanning as we're doing from the north galactic pole down. Let's go back again. This is really, sorry about this. We decided at the beginning of all this to do the scanning and sequence that we're operating in galactic coordinates. So we started up here and we've worked our way down. So these have all been the data releases, 5 of them so far. In 15-degree latitude bins, we're now scanning in this region. So we're just coming down into the plane, DR6, which we hope will be available by probably February at this stage. We're well into DR6 now, but that'll be released. Okay, so that's where we are. And the way we actually just do the photometry very quickly, as I've already mentioned, spatially resolved to take care of vignetting effects. And fundamentally what we're doing, beginning with S-extractor detections, is fitting instrumental magnitudes versus originally Hubble guide star magnitudes, or as I keep saying now, APAS, and doing it in a spatially resolved way, which takes out the telescope effects and, given these very wide fields of view, up to 30 degrees, takes out differing sky transparency. If you have a cloud over here in one part of the very large field plate, you can remove it or allow for it in the photometry. So lots of new things that had to be developed. Very quickly, some of the early discoveries, magnitude variations in giants, subgiants, and giants, not AGB stars where variations are typically seen, but these were things we discovered from K giants that still remain very surprising. They're almost certainly due to spotted activity, but even that is hard to understand on these timescales. Dust accretion events. Here is one from a known binary variable system that produced this relatively short duration dimming, which then recovered not an arc or Bohr star, something much faster than this. Suman Tang worked in this as part of her thesis. And any number of other objects, including a symbiotic nova. We've seen several of these, but this was one that is really quite interesting that I won't take the time. You can look up these papers. So let me now get to what I told you at the beginning was motivating the work that is now going on, namely our survey for the duty cycles, the motivation again being understanding the total population of sources, what fraction of the time are they on, tells us how many we're missing of the black hole LMXBs. So that's what we started doing 3 or 4 years ago. And when we've gotten down to, I won't go back to the slide showing you the sequence of scanning in galactic coordinates, but we did do in the early days, roughly 4 years ago, some scanning of the galactic bulge to understand how well we could do in very crowded fields. This is developing the whole pipeline, and that enabled, once we got going, some of the first, well, in fact, this was the first black hole system to be found in the plate data in quiescence. And there we go again. Sorry about this. This is ridiculous, I know. So here's this GRO 1655 minus 40, showing you that it underwent an outburst back in August of 1945. It was discovered, just as I'd mentioned before, only in 1994 as an X-ray transient. So this was the first one that we found, and not the only one. Shortly after, this system, V4641 Sagittarius, which is a very unusual black hole LMXB. It's unique still in that it is a low mass X-ray binary with a black hole primary, but with a B star companion. So that's because the black hole is more massive than the B star, so it's entitled to be a low mass X-ray binary. It's accreting by Roche lobe overflow, but it's very different in its variability properties. This is the dash light curve, as you can see, going over 100 years, and the system is, even though it's transient, is relatively bright, and its outburst that it underwent back here in 1901 is about a 3 magnitude brightening. I guess I didn't make a blow up of this image to show you the light curve in closer detail, but it's virtually identical to the discovery outburst, which is in 1999 in X-rays and optical. Very, very short duration, unlike most of the others that you're going to see in a minute here, outburst. So this was fun to see. And here's the second one, or the third one, depending on the third one actually, a very interesting system in the halo. This is the first actual black hole LMXB found in the galactic halo, with an outburst that you see here back in 1928, which has a characteristic decay time in optical very similar to its discovery outburst, which was also, it turns out, in 1999 with XTE and, well, with XTE. So those first few got this whole business going. There was one other system, V404 SIG, which is one that was very active just a year ago, with another round of outbursts that are similar to what we see in many of these, not just a single outburst, but several outbursts clustered together over a 6-month period. This one we also see in the dash data, the 1938 outburst, and Sebastian hasn't heard about this yet. With the new scans that we've just now been doing, we see another outburst in 1905. So I didn't make a slide of that, but this is very exciting that we've now got a third outburst of this system. So these are typically 1-month outbursts that we can now look for the remaining 20 or 60, in fact, of all the candidates, which is what we're doing, looking at each of them. The scanning, I'm not going to go back to the scan map, but as you saw, we're just now getting into the galactic plane, or in the region of the galaxy where most of these systems are found. They're not a thin disk population, they're a thick disk population, so their latitude range is plus or minus 5 to even 10 degrees. So we're just now getting into the range of the galaxy where we can actually look for these things. But with these first few, we can do something interesting already, and some of you will have seen this slide before. We can look at the fraction of the time that we could have detected the outburst in order to understand what the duty cycle of each of these 4 systems is. So the yellow shading shows you where, for each system, this is the one I just showed you, the one up in the halo, KV Yuma is its variable star name. That we could have detected virtually any time we looked, because the outburst is very bright. It reaches roughly 12th magnitude. You can see roughly what the long-term light curve looks like. So we could have seen an outburst anywhere that's shaded yellow. The other extreme, we have the first one I showed you, 1655, which is a 16th magnitude outburst. And so we're much less sensitive to that. So the yellow shading, as you can see, is much less frequent. And from each of these, we can see the numbers and the shading for the other 2. We can derive a effective exposure time, 55 years, 34 years, down to only 12 years of effective coverage that we could have seen the outbursts. And so from that, we can define duty cycles for each of these 4 systems, and eventually for many more that will be coming up. And from the duty cycles, we can start to do some interesting arithmetic and understand what these systems individually look like and how they compare. So here you see the total duration that the outbursts typically have. We typically only see the peak of the outburst because they fade away down to, I didn't show here, I should have shown, the quiescent magnitudes of all of these are around 19th or 20th magnitude, well below the sensitivity of the plates. So we don't follow them down into quiescence. But what we can see is typically an outburst duration that is in the tens of days. Yikes, come on, get out of here. And from that, and the coverage, we want to get rid of the, yeah, all right, thank you. I should have just done that. just turn off the... Okay. Good, thank you. Okay. All right, so from this we can derive a duty cycle for each of these, and they're all quite similar, of order of percent. And the systems are very different. They're covering quite a wide range of orbital periods, as you can see here. And yet their duty cycles are surprisingly similar. These numbers have error bars on them, which I'm not showing. These are relatively crude estimates. But they already suggest what we knew really before we started, that we're only seeing these things for a very small fraction of the time, and therefore there are likely, or almost certainly, a much larger population. So the next thing we can do is compare this to what we know from neutron stars, and here it's a much easier analysis to do, and it's not involving the dash data. This is, as I've said here, is involving just RxTE, which had 16 years of 100% coverage, at least on the timescales that we care about for these transients. And these are classic neutron star systems that are the analog of the black hole transients. They're all transients. Aquila X1 is one that I'm sure most of us have heard about, that are popping off typically every couple of years. Not every 50 years, every 2 years typically. So they're very different. And you can see their durations are similar, tens of days. But when you go through the numbers, in this case just measuring directly from the X-ray data, not from the optical data, their duty cycles are at least a factor of 10 larger than that for the black holes. And if we combine these now to compare the duty cycles of the black hole systems with the neutron star systems, we wind up with the surprising result that the duty cycles are a factor of 2 to 6, the factor of 2 to 6 larger in numbers of black hole systems that we see on the basis of their duty cycles, whereas from an initial mass function argument, just taking a very simple salpeter mass function for these things with a index 1.4, there should be only a quarter, in round numbers, as many black hole systems as neutron star systems. So if we combine these two for some estimate of what is the real excess of black hole systems, we get this very large number, which is not telling us that the IMF is wrong. It's telling us that there must be a much more efficient way of making these systems, the black hole binary systems. So that's the first conclusion that we've reached, and the reason you haven't seen this written up is that I'm waiting for more objects to add to the sample. This is all based on a sample of only 4, well, now 5, because we've got an additional outburst for V404 SIG. But let me finish the argument here with some recent new information that is very relevant to this whole discussion, and that is the IMF, the old way that most of us would think of doing this kind of analysis, of taking anything with a progenitor mass greater than roughly 20 solar masses and making that a black hole all the time, and a neutron star, the usual range that most of us have heard about over the years for neutron star production would be more like 8 to 15 or maybe 8 to 20. That picture is changing. This is a recent paper by Stan Woosley's group, which is actually this first author, Sukhold. And what they're showing here in this sort of messy looking diagram is where it is black, you have produced a black hole. This is as a function of mass for a whole series of different models. This is based on neutrinos driving the supernova explosion and allowing the object to either collapse into a black hole or to undergo a core bounce-like event and expel most of its mass. So where you see black in these different models, you produced a black hole, and where you see green, you produced a neutron star. So the picture has changed in two ways, that at masses of 20 or even 26 solar masses, here's a big stripe of green through here, which for their models, which they and others are, this is only, not only the work from Woosley's group, there's similar work that was going on at Caltech, still is. So the basic, and this is the model they think is the best version of this paper now from me roughly last spring. So right away you see that you're making black holes not all of the time. You're not making them at all out of these very high mass ends, but in the canonical 20 to 40 solar mass range, you're maybe making them only less than half at the time. So the previous estimates on the previous slide are actually, if we take this seriously as what is likely producing black holes, these are underestimates, and the overproduction rate of black hole binaries must be even larger. So to me, this is a very exciting problem that is motivating what we're doing with NASH. So what can we do to extend this analysis in a different way? Well, we can look for, if there's this great excess of producing black hole systems, we can look for, and this was again one of the early motivations of this project, for them as just optical transients. Systems that look in the optical like these black hole outbursts, which I've shown you, do, and then of course we have the difficult job of proving that they're black hole systems, which means spectroscopy, obviously, and getting mass functions. So this is what Sebastian is working with me on, and we've been finding, using the survey thus far, a number of interesting candidates. So that's what I'm going to show you next here. We'll go through this quickly. We've found several such candidates. The first one actually was one that George Miller here found a couple years ago, which is a very extreme transient that looks very much like the black hole systems, although its decay time is slightly faster. Again, I should have stretched this out so you can see this more clearly. Well, here it is. In fact, that's easier to look at. So this is undergoing an outburst from roughly quiescent magnitude 17 to a peak brightness here of about 9th magnitude. So about an 8 magnitude outburst over roughly 30 days. So very similar to the black hole systems. If you compare this to AO620, it's actually a very similar light curve. And the spectrum of this system had actually already been taken in the Sloan data. Here's the Sloan spectrum. Here's the spectrum we got on the MMT. And to make a long story short, the object is was not known, nothing was known about this object, but it's a 10.9 day binary period. There is its semi-major amplitude, velocity amplitude, mass function about 0.3 solar masses. All certainly consistent with being a black hole, but with one fundamental difference, which has delayed the paper because more analysis really is still needed. The spectrum, if I go back to it very quickly, here we go, shows helium-2 in emission here. And there it is, of course. That's not seen in the quiescent emission of any of the known black hole systems. Now, it doesn't mean that you couldn't see it in this one. This is a much longer period. The only black hole system that we know of that resembles this is V404 Sig, but it does not show helium-2 in emission. So on that purely observational, basis, this thing is more plausibly a nova, but it has troubles with being a nova, a classical nova as well, which I'm not going to take the time to go into. So we don't know the story on this one yet. So let's go on to other systems, which is what Sebastian and I are working on now. And that I'm going to show you a few examples of systems that are candidates. Here's a 7 magnitude increase. Let's see, this one is, okay, I'm going to go through several of these quickly. So here is a particularly promising one that we've not followed up so far because this one is in the southern hemisphere. We've got a Magellan proposal in to do this one this spring. But this is a very interesting system that is a roughly 10 magnitude outburst very long decay time, so it's not suffering the complications that this one here does, which is very plausible in its outburst amplitude, but the decay time is relatively short compared to the black hole system. So this one is probably not a black hole, more likely to be a WZ Szigety CV system. This one is certainly not that. Let me show you spectra of a few, not without showing you the individual light curves, of some of these that we've gotten recently, just this last spring with the MMT. Double peaked emission lines, very characteristic of these accreting objects, with, in one case, in this case here is the one that is particularly interesting, double peaked emission with full width half max and peak separation values that make it a plausible black hole system, but not yet proven. It could still be a WZ Szigety system. It's a very short period system, only 1.4 hours. You can see the error bars are obviously very large. This was done with the Mount Hopkins Kepler cam, which is not a large telescope, to be looking at a 20th magnitude object with a very short period. So you don't do very well, so we're going to try to redo this. If the period were double this, if it's a doubly periodic system due to ellipsoidal variations, then this could very well be a black hole system. Okay, in view of the time, let me quickly go to the promised brief discussion of some supermassive black hole systems, and beginning with good old 3C273, which I'll remind you, I think most of you know this, this was discovered as variable on these plates back in 1962 or 63. And of course, now that we have this is up near the North Galactic Pole, of course, so this was scanned early on. Here's the full dash light curve in the way you see it on the website. Obviously, large variability. If we replot that with our current tools, you can stretch things out and see the variability much more clearly. The Menzel gap is this wonderful thing that Donald Menzel, the director here from roughly 1958 to 55 to 1968, when Leo Goldberg showed up, or 67. Menzel decided, why are we doing this? We've been taking these plates for 70 years. We can stop, save the observatory some money. And so that unfortunately introduces this blank spot in the coverage. There are a few plates taken in there. It's not totally empty. But in any case, with all of this, we can now do as we can do with anything we're looking at, we can compare when we're looking for variability and whether was the source really doing all this wonderful activity here, or are we seeing funny effects on plates? Well, we do what you would do with anything. We compare the object, here's 273, with comparable magnitude reference stars. So I'm just showing you an image. This is an actual image from some particular plate. I didn't mark which one it was. And once we've done that and we verify that the reference stars are indeed, as they all are, wonderfully constant, there are a few outliers, but within statistics they're all totally consistent. That allows us to put all the data together, and before showing you what a Lohm-Scargill periodogram or power spectrum looks like, we can add more data to just the dash data, which is in green, by using plate data which were not yet digitized by dash, and this is something we're concerned about. There are plates that we have missed. We're going back to get them, but the blue here back in these early days were plates that, as you can see up here, were not coincident with dash. So there are roughly 389 of those plates, so it's a small number compared to the total. So they're missing plates that we're filling in, and we can extend in the black points with much more recent data going up. The end of the plates, by the way, was 1990, 91. There were a few plates, but roughly 1990. So these are all modern data. This comes from Thierry Courvoisier, the ISDC, on 273. And when we have all of these data together, we can make a Lohm-Scargill periodogram. which shows a whopping peak here at a 16.2-year period, which Dan Orazio pointed out to me a few weeks ago, a paper I hadn't known about. This reference here was literally identical to a period that these guys claimed from VLBI data for 273. So it's a very beautiful confirmation, but this is presenting a whole range of new questions because this is all optical data. We're seeing optical data from, we always assumed, the big blue bump in this quasar, and what has that got to do with a period that's discovered in VLBI, which is coming from the jet. So it must be, or presumably is somehow linked to jet precession, or, and more fundamentally, to the jet showing up as a wobbling effect in the disk. But I don't think we understand this at all, and Dan and I are going to talk about this a lot more, but it's a very exciting thing to find. On the other hand, if we look at the other claimed well-known variable blazar as 273, as OJ287, which has spectacular, much more extreme flaring, as you can see here, 3-4 magnitudes, very short durations. And this had been claimed, has been claimed by the Finnish group, Valtonen et al., Savanpa, I can't pronounce his name, and others as showing a roughly 12-year period. So we do the same kind of analysis here. Plot its light curve versus a reference star, and in this case just a single reference star, and then do the same Blohm-Scargill analysis. Well, here something funny is going on. There is a peak at this roughly 12-year period, 11.5-year period that Valtonen claimed, and has a certain amount of justification because on the basis of this period discovery, which was actually back in about 88 from the first analysis of historical data, they predicted an outburst in 2005, which was seen. So that's you know, a nice independent confirmation. Well, the part I don't understand, having just produced this periodogram yesterday, is why this peak is not larger than it is. There are still larger peaks here, which are very different, as you can see. This is roughly a 6-year period or 5-year period. So I don't understand this, but it's pointing the way to a new way from these historic data, this long time series data, to look for these effects in other systems. And as I mentioned at the beginning, there are two other systems, one which Dan worked on, PG 1202-102, that Matthew Graham and company discovered a couple years ago from the Catalina Sky Survey data, a roughly 5.2-year period. Well, that shows up weekly in the DASH data. And another one, which I don't know, Dan, whether you've heard about, but NGC 5548 was claimed in a paper from a few years ago to have a 5,700-day period, and the DASH data show that as well. So I'm not showing you those periodograms because they're still in progress, but there is an effect there in both of these. So this makes it very interesting to think about expanding the search, admittedly to only relatively bright AGN, brighter than 14th or 15th magnitude, to many other systems. Okay, so I'm going to stop there, just summarize here what we've talked about, that we're probing a whole new phase space with this 100-year time domain, and it's very complementary to modern surveys going on, that this is going to allow us to understand the black hole, stellar mass black hole population in the galaxy, because we only see them in binaries. There's no other way of detecting these things so far. Gravitational lensing is not producing these, but we've got this very intriguing result already that there looks to be a much more efficient way of making the black hole systems than the neutron star systems. And that's going to be tested when we get through the disk in the next year or so. It'll take. The disk is, of course, enormously crowded, but this will be a high priority project to understand what this total population really is. And finally, what I was just showing you, that there is a very interesting whole analysis that is possible on either QPOs or genuinely periodic variability in AGN, and separately, but also interesting, which really hasn't been done, looking at the flare size distribution in blazars in particular. Again, back to the fact that you get to look at the most extreme flares with this long coverage. So you don't see those flares unless you looked for 100 years. So I'll stop there. Sorry for going a bit over.
Thank you, Josh. So are there questions? Yes.
Yeah.
Recalibrating your magnitudes going back using the APASS?
Yes. No, everything is done with APAS. So
You've gone right back to
oh, yes. Yeah. No, and in fact, I didn't mention this. The whole way the data processing is set up is relatively easy to reprocess everything, like we're used to thinking about for X-ray data. We could reprocess the whole thing in about 2 days on Odyssey. All of this pipeline is all running on Odyssey, so we have huge resources to draw on. But yeah, the APAS is, and this new release of APAS, which will fill in a lot of missing gaps, is about to come out, and that's going to make a huge difference in all this. Because they're
and you should say why you needed the multi-colors.
yeah,
Because that's one of the things that's really important. We didn't know this when we started.
yeah,
That the colors were going to be important because we don't know
Yep.
the emulsions and they change over time. So
and there's no way of knowing the emulsions,
right,
you know.
it's not recorded.
So yeah, so the color data, which APAS does beautifully, whereas the Hubble Guide Star catalog, well, it was meant to point the telescope, not to do photometry, even though it was both B and R, so there was some crude color data, but not really good enough. Yeah. Anytime.
Stars and sources and dashes, and how many sources do you have?
Of how many sources that we have? What, I don't,
The catalog, I mean, you look at the plate, and the stars, so you generate a catalog.
every individual plate is matched to APAS or the Hubble Guide Star catalog. So in that sense, we know exactly what we're looking at. And of course, every one of those objects is being photometered, if I can make a verb out of it, right? And so we're measuring its magnitude. And the database, which is a big, huge MySQL database, is recording for every one of those objects its magnitude. So you can go back and pull out any object you like and produce light curves like the ones I was showing you. And the ones that we are, for this stellar mass black hole search, most interested in are, of course, ones that are not matched to an APAS star because they're transients. And the APAS catalog only goes down to about 17th magnitude, and these things are all around 20th in quiescence. So we call those dash objects, and there are many of those that are just one-time outliers, usually due to some plate defect, something that is, immediately allows you to throw them out. But when in this blind search for the stellar mass black hole transients, we look for objects, transients, dash objects that have 3 or more points, because you don't get random, associations with even that few number, and that have the, if we have enough points to measure it, the light curve decay times that are consistent with black holes and not with these extreme CVs, WZs, Sagitti objects. So that's the whole procedure that we.
So yeah.
Josh, you
Yeah.
remarked that we have right here the largest of the world's plate
Yeah.
collections.
Yeah,
But there are others around.
there are,
I'm
and
wondering if in 2 years or so, when you're done here, if there are plate collections around.
that's the question that everybody asks us. And the short answer is, if you provide, because there are very large collections. There's a collection half this size, roughly, or more like a third this size in Germany. And the problem is this is labor intensive to run this, and the NSF has been very good to us to support this, but it would require somebody to provide the support, because although everything has been automated as much as it can, you still have to pull plates off the shelves, you have to load them onto the plate cleaning machine that I didn't mention that Bob also designed to clean off those markings on the back onto the scanner, so it's a very labor intensive. It takes 5 or 6 people to run this thing. But yeah, it would be wonderful to do, but
Do these plates
Yeah.
vary in spectral response?
not enormously. They did use filters, red and yellow filters, but the basic emulsion, as Jessica was saying, we don't really know the response, but there were blue sensitive emulsions primarily. But we take that out by measuring, knowing the colors of all the stars on the plates to derive from the calibration stars what the color correction would be for any given object to put it into this band. Yeah. Yes, yes, we have found a number of supernovae, not mentioned here at all, but in Virgo, and this is a graduate student thesis project just itching to be done, to do a Virgo supernova survey to understand the supernova rate in Virgo. But we found half a dozen at least, just without looking, just, stumbling onto them. And it's not been tackled as a complete search, but anyone's welcome to do that. All the Virgo data are all released already. There are, as I mentioned, there are incompleteness in the coverage, which I mentioned in that 273 light curve, which we're dealing with, which is a bit surprising, but that will just fill in more gaps.
Okay. Seems there are no more questions. Thanks, Josh, once again.
Okay. Yeah, thank you for turning off this wireless. I should have done that. I should have done it at the beginning. Yeah, that was silly. Yeah.
Thank you. So it's very interesting.
Josh, this might be a stupid question, but have you